Hi, welcome to HOI's final presentation. It has been worked on by myself, Anna Bailey, Britt Cadena, Mackenzie Cohn, and Liana Teccanelli. And our advisor was Dr. David Elrod. Here's our team slide. Our roles were myself, Anna Bailey, as project manager, Liana Teccanelli as technical lead, Mackenzie Cohn as location advisor and communicator, Ricky Cadena as chief electrical engineer. We stuck to these roles for the most part, but we are also very flexible, and depending on the task we were working on, we kind of switched around the roles. Here's the background of our presentation. The purpose of this project is to design a solar power system for the Instituto Esperanza, a grade school operated by Honduras Outreach International, also known as HOI. It is near San Esteban, Honduras. Presently, the school receives dirty and unreliable energy from the Honduras electrical grid. The school has had to endure frequent outages up to 1 week long, and receiving no electricity for a day is not uncommon. The electricity they do receive is sometimes destructive and has damaged multiple computers at the school. The issues have proved a hindrance to the learning process for the students. The goal of the solar power system is to provide the facility with clean, reliable energy when the conditions are adequate and switch to the utility grid when solar power is inadequate.
Our team conducted a load analysis documenting the power requirements for the solar system. For each component, our team used the power input, quantity, duty cycle, and hours per day of operation in order to calculate the total load. Most of our calculations err on the conservative side in order to make sure our proposed solar system provides power, even when all the components are pulling their maximum load. With the total load of each component, our team was able to calculate the total power that our system needs to produce each day in order to power the HVAC, Chromebooks, lights, and fans located at the school in Honduras. This number came out to be 22,157.5 watt hours per day. With this number, our team was able to move forward with choosing the other components of our solar system. The peak load was calculated to be 23,707.5 watt hours per day. This value will help to determine the size of the inverter chargers. One of the first actions our team took was to conduct an HVAC cost analysis. Currently, there are 2 HVAC systems in both the computer lab and the library. The library uses both units at the same time to cool the building, while the computer lab only uses one at a time to cool the room. Our team decided to look into the cost of powering the current HVAC units and compare it to the cost of powering and replacing the HVAC units with new, more efficient ones. The following factors we considered are cooling power input, cooling capacity, estimated cost per watt of the solar-powered system, and lifetime of the current HVAC systems. It is important to note that the client is currently happy with the performance of their current HVAC units. Based on our analysis and our research, we concluded that the best option for the client is to keep the current system. When you factor in the cost of the unit and the price per watt of new HVAC units, not much money would be saved, if any. We also considered other factors, including installation, which would only add to our argument for keeping the current system.
This is our initial conceptual design. Its detail is furthered through our interface analysis later. The basic concept is the same as most solar panel systems. The solar panels are connected to a charge controller, which feeds into the batteries, and from there it goes into an inverter to supply the power to the school. The inverter converts the current from the batteries from DC to AC and then delivers it to the computers. This combination of components protects the computers from power surges. The upper inverter charger acts in between the city power load and the batteries, can either draw power from the batteries and the solar panels or put power into the batteries from the city power lines. This is why the design shows the arrows as bidirectional. This design function allows for the system to switch to utility power when the batteries fall below a certain threshold. When functioning properly, the lights, fans, HVAC load, and the computer load are all being powered by the solar panels, each through their shown inverter charger. When the solar panels are not providing enough power or are offline, the lights and fans and HVAC are powered directly from the city power, with it passing only through the upper inverter charger. There is no need to make sure that the power being provided to these devices is clean, which is why the device shows the HVAC, lights, and fans directly tied to the upper inverter. The computers will take the power that the upper inverter puts into the batteries after it runs through the second inverter charger, thus ensuring the power going to the computers is clean and they are protected from power surges. Fuses and breakers have been purchased and their placement will be decided on the ground.
All right, and here we have our component selection for the solar power system. So all of these components have already been purchased, and the solar panels and the batteries are on site, and the charge controllers and inverters will be brought by the mission team. So our system will use 24 315 watt solar panels. For batteries, we'll be using 20 12-volt 200 milliamp hour gel batteries. We will be using 2 charge controllers to connect the solar panels to the DC bus, which I will talk more about in the next slide. And finally, we have 2 inverters that will be used for the system. They're both 600 kilowatt hours, and they give 120 volts AC. All right, and this slide shows how all the components are kind of like interfaced together. So we have a picture of what the buses kind of look like on the right. They just connect the things basically. All right, for the first AC bus, it connects the city grid to the first inverter charger, and that first inverter charger will deliver power to the DC bus and also to the HVAC fans and lights. The second AC bus is just to the computers, and that's connected to the second inverter charger. And then the DC bus will receive power from the solar panels, which are connected to the charge controllers, and it will also be connected to our battery bank, which will be operating at 48 volts, and that will be receive power from inverter charger 1 and deliver power to inverter charger 2.
In order to mount the panels, our team decided on a corrugated rail system. The clamp mounts will be used to secure each individual solar panel. Using this system, the solar panels will be aligned in a 4x6 matrix in order to accommodate all 24 solar panels. It's important to note that the following figure is not drawn to scale. Our team knows that the length of the roof is 59 feet, but for the width, we estimated this number using other dimensions that were given. The rails of the mounting system will run parallel to the width of the roof and will be secured to the purlins of the roof. Our team chose the shorter length for the rails so that the rails would be less likely damaged during transport. It's important to note that if the mounting system is made of a different material than the aluminum solar panels, corrosion will occur. So to prevent this, we could either use rubber washers to prevent the 2 materials from coming into contact with one another, or we could use a corrosion-resistant spray. The batteries will be secured in a shelving unit in the corner of the computer lab. The charge controller and the inverter charger will be located right above the batteries in the same unit. All of these components will be covered and inaccessible to children for safety reasons. As for the load distribution of the solar panels, each of the solar panels weighs 58.4 pounds. The total weight of all 24 panels is about 1,402 pounds, with a distributed weight of 2.9 pounds per foot squared.
Next, our team completed a maintenance report. The objective of this report is to help HOI maintain the solar components and troubleshoot when the system is down. To maintain the panels, they should be free of dust or other debris. About twice a year, the panels should be wiped clean in order to obtain good efficiency. The panels can also be replaced individually without altering the rest of the system. The panels should last up to 25 to 30 years. And additionally, the surrounding area may need to be checked for trees that may grow and cast a shadow across the panels. Also, the batteries have to be watched because they have the shortest life of all the components. They are expected to last between 3 to 5 years. They can be replaced individually without altering the rest of the system. The batteries can be maintained by reading the levels of the charge controller. The battery levels can also be monitored by disconnecting the batteries and reading the voltage across each terminal with a voltmeter.
There will be a trip in May to decide how safe it is to travel. Also, the trip allows for more load analysis to be done on the chosen route. There are decisions that are dependent on the site in Honduras. When the team arrives in July for installation, these final decisions can be made. Our team has designed the solar system to be expandable. In the future, if in the future, the power demand of the school in Honduras increases, additional solar panels can be installed to provide more power. Thank you so much for listening to our presentation. Please let us know if you have any questions.